Yeah, tell me.
Sir, you took a function f which depends on xyz and you done the differentiation there and
Yeah.
you took f common to make del operator.
Yes.
So till now we haven't do this type of things. So can you explain if there is a theorem or anything else in which we can separate the del and the that quantity for which we are making the change? So please tell us.
Yeah. So you say again. So you asked me to give some. So so actually the proof. I mean, are you asking for the proof? So what
Sir,
proof?
not the proof. Sir,
Uh-huh.
you took their del and the like dt, you took d and t separately. You took t common for making the del operator.
Oh, okay. So what I had here, dt equal to del t by del x and mm, x cap plus del t del y cap plus del t del z cap, and then I took dot product dx x cap plus dy y cap plus dz. This thing we had.
Yes, sir.
Okay, instead of I cap, J cap, K cap, I am now writing X cap, Y cap, Z cap. Okay, so I may mix this X cap, Y cap, Z cap, and I cap, J cap, K cap is fine. Okay, in many exam paper also you may find like this notation also. Okay, so yeah, so then what I did, I just took this T from here. Okay, and then I wrote like this. T here, and then took dot product, right?
Yes, sir.
Okay, and then actually I wrote this x cap on this left side just to uh, uh, just for the
Right confusion.
right. Now I have a lot of space. T dot product. Okay. Do you agree with this, or you had doubt here?
Sir, I have doubt here where you put the t common.
Okay. So yeah, it's just the. I mean, you have dy by dx. In high school we take, okay? Can you not write this is equal to ddx of y? Okay, that's what I did.
Sir, d here represent the change. Like for the change dx, we take x final minus x initial. Then we write del x or dx. So this represents the change, and we cannot separate it.
What you no here I wrote outside just to I mean I mean, so basically this t will be multiplied, okay? Or if you do not like that step, you can keep t here, you can keep t here, and then that quantity you can call is the grad d, okay? Doesn't matter, okay? So it doesn't matter how you write. The point is that grad of any function f is a vector quantity, and this is equal to del f by del x, okay? X cap plus del f by del y cap plus del f by del z cap. Okay, I can write this, I can take f common. Okay, it's okay. I mean, there's nothing wrong. Okay, all is fine. So when f is outside, so it will be operative. Okay. You have lot of terms and the same term appears in all the term. Same function appears in all the term. You take that as common. Okay. You cannot write t on this left side. Okay. You cannot write this one is equal to like this. Okay. This is wrong. So first few, first 1 or 2 week, you have to be very careful. Okay, you have to learn the vector analysis very precisely. Okay, there are very slight difference in equations. Okay, that will make your final result completely different. You cannot write this thing like this. Okay, here also I took common. Okay, but the difference between this one and that one is that here writing f means it is multiplied. Okay, it's like this. It is an operator. Okay, this is an operator. Okay, I don't know. So this is an operator. So this one you can write. Okay, f del. This is del operator. Okay, so this you cannot write. Okay, this is not equal to this quantity is not equal to that one. Okay, because this is grad f. On the other grad f, sorry, this is grad f, but this one is f grad. Okay, so f grad is not equal to grad f is not equal to f grad. Okay, this we agree. Okay, so you have to be careful, like where this operator is sitting. Yeah. So here this is not an operator anymore, because after this operation, after this differentiation is done, this will be just your this coefficient will be just a normal coefficient. They are not operator. On the other hand, here operator. Okay. So if you multiply function on this, then it will operate. Okay. On the other hand, here the operation, the differentiation is done. Okay. So it is not an operator anymore. Okay. So that's why this grad f is not equal to f grad, although they are vector. Okay. This grad operator, gradient of this basically del operator. Okay. This is gradient. Okay. So I'll now tell the physical significance of gradient. Are you happy now? Is it better a little bit?
Yes, sir.
Okay, the proof of the few steps that I did in the last class will naturally come from this Taylor series expansion. Okay, so in your mathematics course, you will learn Taylor series and many application of that. Okay, it's just this Taylor series expansion. Okay, just function t, which is a function of x, y, z, you just expand it in Taylor series, and then you take the change in t. Okay, it's just 2-3 lines of calculation, but you need to know the Taylor series. Okay, so this one is equal to this one. Okay, grad t dot dl, right? So that we got yesterday. The last week. Okay, so now this one I can also write grad t is mod. So here we have vector and another vector, their dot product. So that I can write as the magnitude of this quantity. Okay, magnitude, let me write in this way, and then here is another magnitude, right? Probably you write a magnitude in different way. Okay, this is the general notation. Okay, and then the angle, the cosine of this angle. Okay, theta is the angle between this dl vector and the gradient of t. Okay, so then grad t is mod is equal to dt over dl mod, right? And then you have one vector, right? Now, if this vector, now this angle, okay, so note you have a dl vector and you have this grad d, this grad d, okay, we have two vector. Now so you have a function, a scalar function t. T is a scalar function. Okay, it can depends on your space coordinate x, y, z, like temperature. Temperature in this room are different. Okay, so you compute this grad t. It's easy to compute. Okay, you compute this quantity and then you see in which direction. Okay, so dl is your direction. Okay, so dl is an arbitrary vector. Okay, so you point. Okay, so this is your let's say this is your grad t. Okay, this vector, and so this is your, let's say, dl vector. Okay, so dl vector you change. Okay, you change your dl vector and see in what direction this quantity is maximum. So this quantity will be maximum when, so cos theta is equal to no, what I mean, this quantity, you see when this maximum dt, when this quantity change in t actually, yeah, so this change in t dt by dl is maximum when
Cos theta equals 0. Cos theta
what?
equals 0. When cos theta equals 0. Cos theta equals 0, sir. Maximum.
Cos theta, no, so what I
Parallel.
what I wanted to write. Okay, so let me write. So I want to see this quantity, okay, dt by dl. Okay, this is equal to grad t. Okay, this mod, and then the cos theta. Okay, right?
When cos theta equals 1.
When
dt
cos theta is equal to 1.
upon what dl is maximum.
I wrote it in some confusing manner. Okay, so so basically what you do, you change. Okay, you change the direction of dl. Okay, and you see in what direction the change in this function t is, rate of change of this function is maximum. Okay, so you can easily find that you have to align your vector. Okay, your arbitrary position vector along the direction of dt. Okay, so basically only when this one you align along this grad t, you will see the maximum change in t. Okay, so the physical interpretation of the gradient is the, I mean, of course, any vector has magnitude and direction. So what is magnitude? Magnitude of gradient, it gives the rate of change. Okay, it can be increase or decrease. Okay, rate of change of this function t. Okay, is the basically the local slope. Okay, rate of change of that quantity is actually the slope. Okay, so the rate of change of the function t. Okay, and what's the direction? Direction will be the same in which the maximum change occurs. Okay. You followed?
Sir.
No, sir. What are we doing
Yeah.
here? I'm not really sure.
So gradient of a function if let me write. Okay, so the magnitude. So if you have a function f, what will be its gradient? Okay, so obviously this is a vector. Okay, it is a vector. vector, okay, whose magnitude is given by the its magnitude will be given by the rate of change of the rate of change of this function f, rate of change of f, okay, and its direction and the direction is same as the direction in which the maximum change occurs. I don't know whether you can read this lower part, but I mean, whatever this equation tells, I just wrote here. Okay? So in one dimension in your high school, you had actually, if you write this quantity, then so in one dimensional case, what we had, dt is equal to del t. If you can write this equation, let's say t is a function. Sorry, no, this is just scalar. Let's say function of x only. Okay, t is just a function of x only. Then del t over del x, and then x cap, okay, dot dl vector is x cap
dx.
dx. Okay, so you have x cap dx. So then you have x cap is 1. So del t over del x dx. Now here the fact is that t is a function of x only. So the total, I mean, you don't have to use this partial differentiation. So you can straight away use the total derivative. So dt over dx, okay, this quantity, and then dx, okay, which was actually the dt. Okay, so I just extended the knowledge that we had in one dimensional case. Okay.
Yes, sir. Yes, sir.
The point is,
Okay, sir.
have a function. Okay, let's say you are I mean, you have gone to this near some mountain area, okay, some hilly area, and you have, let's say you have some instrument, okay, and which is giving the reading of height, okay, at different point. Okay, now on the surface of earth, what are the two coordinate? Latitude, longitude. Okay, latitude, longitude are the two coordinate, and of course if you go higher, I mean, if you go above the surface, your height increase. If you go below the surface, height decrease. Okay, so you have a quantity, height, let's say. So instead of function f, now you have a height. Okay, okay, so your function is now height, right? You have gone for tracking, and you have a very fine instrument which is giving the reading at latitude we call theta, okay, and longitude. Okay, longitude, you know, do all of you know longitude?
Yes, sir.
Yes, sir.
Yes,
sir.
on the
Yes, sir.
surface, your this GPS actually use these two coordinate, latitude, longitude, okay, to define the position, your precise position. Okay, so so then you have a I mean, you have got you are getting the reading. Okay, different location you are getting that different values. Okay. Now and you are very smart and you have just fitted those data and you have got a function. Okay. Let's say this is equal to theta q minus phi plus theta phi. Okay, you have got this value. Okay, this is the functional form. So if I take theta equal to 25 degree, phi equal to 0 degree, you'll get one value. If you take phi equal to different, some other value, you'll get different. So at different point, your height are different. Okay. Now you want to go for trekking and you do not want to take difficult path. So what you will do, you will of course choose the path in which the rate of increase of age is minimum. Okay. It is not that steep.
Yes, sir.
Essentially, this quantity, what this gradient give is the steepness of the function. If you have a height, how rapidly height increase. Okay. Obviously, the height will not increase at the same rate in all direction. Okay. Let's say there is a mountain on this side, so the height will increase on this direction. Okay. Right. If you go, perpendicular to that direction, no, so then the height will not so the height will not change. Okay, so different direction, the rate of increase of height will be different, and this gradient of this function essentially give this how rapidly the quantity change. Okay. So here in this case, you can so there's a problem given in Griffith. Okay, there's a exercise problem. You can work it out. Okay, so how much is the steepness of this age, and how high? So if there is a hill, what is the top of that hill? Okay. So how to find the local maxima and minima of a function? What you do?
Sir, which expression represent the gradient of the function, that dt by dl?
Gradient? No. Okay. Magnitude is this one, but it also has a direction. Okay.
Sir, which one? That last equation.
Yeah. So last is either you can use this one or that one. Okay.
So which is the gradient in both of these?
Okay. So this is the general formula. So when so this is also general formula. It's fine. Okay. So this one is the magnitude of the gradient. Okay. Look, any quantity, any vector quantity has two components, essentially two information. One is the magnitude, another is the direction. Okay. So the direction is taken care by this factor now, cos theta. So you should not forget this factor. Okay. So this factor is actually telling that the rate of change of this gradient is actually maximum along the direction. Sorry, the direction of gradient is the direction in which the rate of change of this function is maximum. Okay. Now, if you want to ask like which one is the most general, is this one. Okay.
Sir, I wanted to ask that dt is the magnitude of gradient, or dt by dl is the magnitude of gradient?
The magnitude of gradient is dt over dl. Okay, dt over dl is the magnitude of this gradient, but this magnitude is along the when the cos theta is 1. Okay, its magnitude will also be different. Okay, in different direction. As I said, the steepness of this height, okay, will be different in different direction. Okay. So
Okay.
magnitude is dt over dl only when you are computing this quantity along the direction in which this function change maximum, function change at a maximum rate.
So gradient is a vector. So is that vector represented by del of t? The del operator of t, is that the vector, gradient vector?
It is a vector. Gradient of any function is a vector. That's why I wrote this vector with the dot product with another vector. Okay. I wrote this definition just to get some physical intuition of the gradient.
So that del t is the gradient vector.
Del t is the gradient vector. Okay. Del t is the gradient vector. Del is a del operator. Okay. Del is so-called del operator. It is a vector operator again. Okay. Now grad t is the gradient. It is a vector. Gradient of t. Okay, it is better to call like gradient of a function t. Okay.
So why did we look for maximum there, sir? Cosine theta we said.
Good questions. Otherwise, you can call it. You can just keep it then like this. Okay. What is the magnitude of this one? Magnitude is dt over dl and then 1 over
Cos theta.
yes. Yeah. So then you have this quantity. Okay. Then you can call this way. Okay. Magnitude of this vector is equal to dt over dl and this is the angle. Okay. You have to also take care. Okay. I just get rid of this vector. I just want this one is 1. Okay. And just see how much is this. I mean, what is the maximum? I just look for this quantity. This I made it maximum. Okay. When this quantity is maximum, dt over dl, when this cos theta is 1. Okay. Because of this angle, I told, because of this angle theta, okay, you will get different values of this quantity, different values of this quantity in different direction. Okay.
Yes, sir.
So in Griffith, there is a very nice exercise problem. Please do it. We usually put it in assignment. Okay. Even if you do not want, then you have to do it. Okay. Okay. Now I'll take a few just at least take 1 or 2 examples. So let's take a function t is equal to, let's say, x square. Okay. It's a valid function. I'll just take a one-dimensional case. Okay. Right. So this is a valid function. I will take gradient of t. How much will be the gradient of t?
2x.
2x.
Yeah.
2x.
So I'll this grad and then this x square. Okay. So here you have a del x, and then you have only x dependent. So this term will be important. Okay. So you multiply. So you put x square here. So then you'll have a 2x, and then x cap plus you put here x square. The derivative with respect to y, it will be 0. Derivative with respect to z, it will be 0. So you get this quantity. Okay. Now, if you want to make a plot of this function, so what do you get then? Let's say here is your coordinate x, y, and z is perpendicular to the board. Okay. Let's say put it z in this direction. Now, this function, gradient t, is of course a vector. Okay, you see this x cap. So gradient is t is pointing along x direction. Now what this vector is 2x. So when x is equal to 0, it's a null vector. Okay, it's still a vector because it's magnitude 0, but it points along x cap. Okay, along x axis, and then
X-axis.
increase as x increase, the vector magnitude increase. Okay, like this. And then as again when x, let's say x is equal to 1, this is 2. Okay, the coefficient is 2, and then when x is equal to 2, so 2 into 2 is 4, so your magnitude will be double. Okay, right? So again when x is equal to 4, you get 8.
Sir, how can a null vector can have any direction as it is?
How can
Yes,
A
sir,
null
it is a
vector can have
point.
direction.
a null vector has a direction? That's a good point.
That is just a point or not a point as well. It is nothing.
So so it can, I mean, it has a direction. So so you can think in a way that that the quantity, let's say you have a velocity of a particle, so it has it has actually changed. I mean, its velocity has gone to 0, but it still has actually its direction. Yeah, actually, I don't know how to say it in better way.
So now we can say that gradient of t becomes a vector field.
Yeah, when you take an example, is very obvious, and you can pictorially plot. I mean, pictorially visualize this function. I mean, gradient. So t you can plot. Okay, is x square. Okay, and so when it has only x dependent. So as x increase, this quantity increases rapidly. Okay, if x is 0, is 1, 1, 2, so 4, so it rapidly increase. Okay, along x direction. It has no other dependent. Okay, and then when you take its derivative, it's actually the first derivative essentially. Okay, but it has a direction. Okay, there's a concept called directional derivative. I'll tell you what it is. Okay. Okay, so this is one example, and you take this example as well. So a quantity t is equal to let's say just 1 over r. Okay, you take this one. Can you read this 1 over r? What is r? R is
Magnitude of r vector, radius vector.
yes, that is the square root of x square plus y square plus z square. Okay. So you can see this part, right? So r, magnitude of r is equal to x square plus y square plus z square, or you can also call this as L. This is r, but you can sometimes also call it L. Okay, L vector is again the same thing, the position vector. Okay. So you have a function which is equal to 1 over square root of x square plus y square plus z square. You compute its gradient, and then you yourself convince yourself that this function, the gradient of this function is actually pointing towards the center. Okay. So here the arrows are going, on from left to right. Okay, from the origin, but on the other side again the value will actually go in this direction for this function. On the other hand, for this function, the gradient vector will actually point towards the center. Okay, you can do it yourself. Okay, now there's one more concept called directional derivative. Okay, so it's a derivative. I mean, derivative you usually take. What you need to do, you again you see this dt over dl. You get something dt over dl. Okay, but essentially the gradient of a function t is actually the dt over dl with some direction. Okay, so directional derivative derivative. So directional derivative means the derivative of a function along a particular direction. Okay, along a direction, let's say n cap. Okay, so what is this one of directional derivative? This is a directional derivative of a function t. Okay, then what you do, you take grad of t and then just take dot product of n cap. Okay, is clear?
Yes, sir.
So directional derivative means you have to take derivative of that function, okay, with a particular direction. Okay, as I said here, you can have different magnitude of gradient of t in different direction. Okay, I was saying that it will be maximum along the direction it will change occurs. But if I tell you you have to compute the directional derivative, okay, of a function along a particular direction, then you just compute grad t, take a dot product, then you get just a pure scalar quantity. Okay. Yeah. So someone is asking a question.
So sir, we are just taking a component of grad t.
Component of
derivative. Grad t. Sir, in directional derivative.
Yeah, exactly. Projection. It's the projection.
Projection. Yes, sir.
Exactly. Very good. Okay, so this much is I wanted to say about gradient, but
Sir, I have a doubt in the gradient part. So when you proved that when you told us to vary dl vector, so for a particular point, how can we vary dl vector? Dl vector will be constant when we fix the reference frame, right?
Yeah, when you fix, of course, when you fix it is okay. But so far my discussion was based on an arbitrary vector, arbitrary position vector L. Okay, and I change its value by an amount, dl. Okay, so it is my arbitrary direction. So here it's basically the same type of thing. But you have a fixed direction. Okay, in that case you have to compute this quantity, and that is the directional derivative. Okay, again this is the same thing. Dt, instead of this quantity, instead of dl vector, you have now n cap. Okay, and then you get this quantity. Okay. In general, it is not. Okay, I said. What I varied L, I varied the DL just to get, I mean, just to see like in which direction the value will be maximum. Okay.
Okay, so in that case, you are also varying, you are also changing the reference frame or translating and rotating the reference frame also.
No. I'm not changing the. I'm not. So my reference frame is fixed. XYZ. The reference frame is fixed. So this dl vector is an arbitrary vector. Okay. The direction. So as I said in that plot. Okay. So you have this dl vector. Okay. So that you change. Okay. And change in different direction. Okay. And you see in which direction this grad d is maximum.
Okay.
Okay. So as I said, when you are working on this hilly area, you have different height at different point, and you can gradient of t will actually tell you in which direction this quantity, the height, in this case, will have maximum increase. Okay.
So, sir, in that case, if you are changing the x, y, and z coordinates, del t is also bound to change, because if we assume t as a scalar field, it is going to vary
That's
also.
what I'm saying. I'm not changing the coordinate system. I'm not changing x, y, z. My coordinate system is fixed. What I'm changing, my position vector. Okay. What is position vector? Okay. So R, you usually call it R. Okay. Here is not R, is L. Sorry, L. This is equal to x cap plus y cap plus z cap. Right. So this is, let's say this is your yeah, this is your L. Okay, this L vector. Okay. So this depends on x, y, z. You can have position here, you can have point here. Okay, x, y, z is arbitrary point. Okay, I take 1 1 1, I take 2 1 3, I take 2 2 2, 3 3 3 like that. So I can take different point. So your this position vector, that is going to change. Okay.
Okay, sir.
Yeah. So okay, one more thing I'm forgetting. So grad t, if the gradient of t is 0 along a particular direction, let's say, okay, let's say I mean, of course, this grad t. So you take this previous example. You remember I took x square. So that was 2x x cap, right? In previous example. So obviously it is 0. It is 0 at x equal to 0. Okay. And in your high school knowledge, you know that if a function, its first derivative is 0, then it has either maxima or minima. Okay.
Yes,
So
sir.
here the grad t is equal to 0 will tell there is a local minima or maxima. Okay. So in this this mountain example, we had a height, and if you find that grad of this height h, grad h is equal to 0 at a particular point, okay, then that means that there is a that is the top of a mountain, okay, because it has a local maxima. Okay, height has a local maxima. Okay. So
Okay,
that is a useful quantity. Okay, but that is not necessarily true everywhere. Students actually make a mistake that grad d is equal to 0. No, may not be possible. Of course, it is not possible everywhere. Okay, if t is a constant quantity, let's say t equal to 2. Okay, just t instead of x square, let's say it's a 2. Okay, of course, grad d is equal to 0 everywhere. Okay, but we may not have that case. We may have a particular point, yeah, where grad t is 0, okay, and that gives an indication of local minimum or maximum. Okay. Okay. So now I need to discuss divergence. Divergence. Okay. So now divergence, you already by the name you got some idea that you have heard this term divergence in different contexts. Okay.
Yes, sir.
Yeah. So diverge, of
In
course, you know.
functions.
Yeah. So if essentially it gives the how much the quantity diverge. Okay. Now let me give this definition of divergence. So now divergence is it is del dot A. Okay. Now A, B, C, F and T we very frequently use without telling what it is. Okay, it's a general quantity, general function. Okay, a general field. Okay, in general it is three-dimensional, and A, B, C. When I take A, B, C, they are usually vector. When I take F or T, they are scalar. Okay? So this is the definition of I mean the mathematical definition of divergence. Okay, This is a del dot vector. Okay, so this is the divergence of a vector. Okay, so this is the divergence of a vector A. Okay, now this operation is a dot product. Okay, now again here you have to remember. Okay, note del dot A is not equal to A dot del. So we had this dot usual this dot product A dot V is equal to V dot A. Okay, that we write. Okay, it's just the cos theta angle. Okay, angle between A and V. So it is this operation is commutative. Okay, but here this you cannot write it this way. A dot so del dot A is not equal to A dot del. Why? Why you cannot write?
Sir, A dot del will give another operator.
Yeah, exactly. So here this function is still hungry. Okay, if you put a function, then it will operate here. But this is not I mean this is not an operator. Okay, so explicitly I'll write it. Here I'll write here del dot A is equal to del. So again, this one is x cap del del x plus y cap del del z plus. So okay. Let me write one more step. Okay. So this one is x cap del del x plus y cap del del y plus z cap del del z dot product x cap ax plus y cap ay plus z cap az. Okay. So this is equal to del a x plus del a y del y plus del a z del z. Okay, this you need to remember. Okay, so del dot a is equal to this much. Okay, now now let me take an example. Okay, things are very easy if you take example. Okay, so I have space here. I utilize this space. Okay, so let's take A. Now I have to take an example in which A is a vector. Okay, so give me a very simple vector. Let's start with this x square. So earlier I took x square. Now here is a vector. Okay, let me take this example. Okay, so then this one is how much? Del dot A. So
2x.
So ax is
2x.
So you put x square here, right? Then you have del x square, and then plus 0. So then we have 2x. Now you got a scalar quantity. Earlier we got a vector quantity. Okay. So now you can make a plot of this quantity. Okay. So of course it all depends on the value of x. So if you consider the positive x side, this is x, this is y, this is z. Now x is equal to 0, you have 0, all these values are 0. X is equal to 1, you have value 2, and then 4 like this. So the values increase. So values are positive. Okay. Del dot A is greater than 0. Okay. The value is positive. Here on this side, x is negative. So del dot A is less than 0. Okay. Now what does this mean? So divergence of A actually gives so better I now I can also make this this pictorial view of this vector. Okay. By the way, vectors are sometimes very easy to realize if you make it I mean, if you give it geometrical interpretation. Okay, so basically just give some geometrical picture of the quantity. So here we x square x square. So the dx is a vector, its direction is x square. So now you can, so when x equal to 0, it is 0. Okay, when x equal to 1, it is 1. Let me take this color.
Excuse me, sir.
Yes.
Sir, why del A is not equal to A dot del? Explain with the example.
I'll come. Just focus this point.
Okay, sir.
Okay. So this vector I'm plotting. Okay. Do you agree with this plot? When x equal to, let's say, 1, 2, 3, so 9, so it will have 9 value. Now you yourself think from x equal to 0 to the right side. Okay, when x increase, you see the magnitude of this vector A is increase, right?
Yes, sir.
So that means there is a something that is diverging. Okay.
Sir,
Something there. So this so later you will see, you will realize that there is some source. Okay, and because of that source, the quantity will diverge. Okay. So on this direction, divergence of A is positive. Okay. So once you make a pictorial view of this of your vector, you can easily answer the its divergence. Okay. On the left side, it will have negative. Okay. So that also you can yourself convince. Okay.
sir,
Yeah.
what is the use of divergence?
Yeah, so divergence is very useful to check how the vector is changing in different direction. Okay, I mean, so again, it's a derivative. Okay, so all these we are doing the vector differentiation. Okay, when you have a scalar, you can take differentiation. Okay, that will give you a vector quantity. Okay, so the gradient of f or gradient of t that I did earlier. Now, when you have vector, you can take you can take apart this del operator and you can have a divergence, and the divergence is useful to check whether there is any divergence of the function or there is a convergence. Okay, or it's a uniform. If the vector is a constant vector, okay, if the vector is a constant vector, then it will have zero divergence. Okay, you everywhere same. Let's say velocity of particle. Okay, let's say it is not changing at different location. The velocity is same. Let's say velocity A is equal to, let's say, 2x cap plus 3y cap plus 5 z cap. How much is divergence? How much is del dot A?
0.
Del dot A is equal to 0. So this is a vector A. This is called constant vector, by the way. Okay, constant vectors. Have you heard this constant vector?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Vector A is equal to ax x cap plus ay y cap plus az z cap ax ay Az all are constant. So student usually make a mistake, they just keep one direction. It's wrong. Okay. In general, they can have all three direction, but the components are constant. Okay. So this for this constant vector, divergence is 0. Okay. But we can have a space dependent vector, like in this case, x square x cap, its divergence is 2x, but its divergence is 0 at x equal to 0. Okay. So there is no there is no source or sink. Okay.
Sir,
Yeah.
sir, can you please explain the difference between usage of del operator with scalar and divergence, sir?
Okay. So now some difference you can yourself identify very easily, that when you have a scalar, basically it this gives the change of this function t in basically in all direction. Okay. And the maximum change will happen in a direction in which the sorry, the direction of this f will happen in the direction in which not f t increases maximally. And this is a vector quantity. Here you have a vector, and how to actually take, so obviously you can take a derivative del a by del x. Okay, that is also a valid quantity. Okay. You can have a del a by del y also you can compute, del a by del z also you can compute. But here this one is actually giving the the change of this vector along all direction.
So we also have another class right now.
I realize that. I realize this. Okay. So what is the time in this?
Sir, can I ask one doubt? Sir, I wanted to know how is del dot A different from A dot del?
Ah, yes, someone else actually asked that. Del dot A, this one?
Yes, sir. Sir, can you write it explicitly?
Yeah, so this is, this one actually gives the change of this A.
Yes, sir.
Yeah, so this gives the change of this A with respect to all coordinate. Okay.
Yes, sir.
With respect to all coordinate, you see the del del x, del del y, del z. Okay. But this one is just a dot product of two vector. Okay. Of course, it is also dot products in some sense, but this does not give a change. Okay. It's still an operator.
Okay, sir.
Still an operator. This one is equal to ax del del x. This one you can write this one ax del del x plus ay del del y plus az del del z. Okay. This right hand side. But left side is this one. Okay, this one. Okay, so you can leave. Have questions you can say. Others can leave.
Sir, where can we say that the function is divergence or convergence?
Yeah. So the function, either the function has divergence or convergence, you can check by computing this quantity. Okay. Compute del dot A, and you take different point and check this value. Okay. Like here, on this right hand side you have divergence. Okay. The function has positive value. Okay. This has divergence on this side we have convergence because del dot A is less than 0. Okay. at point x equal to 0, there is no divergence or convergence. Okay.
So can we say that
Sir,
if
how
the
can we
value
say that at the left of the x-axis there is convergence because the value is continuously decreasing. It is not tending to some value.
Oh, sorry. Yeah, that's right. Sorry, my mistake. Sorry, my mistake. Yeah, so actually it is yeah, so the value is actually so negative. Yeah, so this, yeah, so in that.
Sir?
Better you think yourself. Okay, so so here you have more negative and yeah, so it is actually it is it has
Sir?
divergence. Yeah, tell.
Why have we made all those like vectors? Del dot A is not a vector, na?
Del dot A is not a vector, it is 2x. Here.
Sir, so it must be a straight line. So why have we made arrows on the?
No. I was showing this A equal to x square A. I was plotting A, vector A. I was plotting vector A, not divergence of A. Okay, it is not this one. The vector A, this one I was plotting. Okay. On this other side, we'll have yeah. So we have when x equal to negative, it will have a value. Divergence is negative. Whether your time is running, you can leave and then we can continue this thing tomorrow. Because I do not want you to miss the other class. So when x equal to let's plot. I'll plot this. Okay. I'll discuss this maybe tomorrow. Okay? We can leave. So,
Is there any lab class today?
So convener should communicate you all. Have you got any information?
No, sir, not yet.
No, sir.
Okay.
Okay.
Yeah, I'll take. Yeah, so you should get some information. I'll check that when the lab is starting and all. And the tutorial most likely from this week the tutorial will also start. Okay.
Sir, what will happen in tutorial class?
You will come and see. Okay, so yeah, you don't have to be prepared for that. Okay, at least for the
Sir, who
first.
will take the class?
Sir, do we have a tutorial class today?
No, tutorial is on Friday.
Sir,
No, sir, it's today.
This
Today we have
Today's
chemistry
labs.
tutorial.
At
But
what
we
time?
So
haven't
today's
seen
lab class.
yet from the
Yeah,
Yes.
the tutorial is on Friday. Tutorial is on Friday, I think. Maybe today there's lab.
Sir, also.
Oh, by the way, someone was saying that why don't you share this this class code.
Yes, sir.
You have idea how to get this class code?
Sir, if you just go to Teams and then Settings, if you press the three dot in the top right corner.
Teams, wait, so. Okay, so team setting, okay. And
In manage channel, no, not in manage channel.
Account, privacy, notification, device, permission, voice call. Okay. Yeah, leave it for the moment. I'll myself.
So it's a very confusing interface.
The problem is we don't use Microsoft Team, so we are using only for this this class simply because it has more than 100 students, and Google Meet doesn't allow, I think, more than 100 student, 100 participants. Okay, so you can join the other class. We'll discuss tomorrow, and I'll figure it out if I get and continue.
Sir, what about attendance?
What about
Attendance.
attendance? Attendance I randomly take. Okay, so some days I forget, and I usually randomly take the attendance. I'm download the file. Okay.
Thank you, sir.
Thank you, sir.
See you tomorrow.
Thank you, sir.
sir.
Thank
Thank you, sir. Thank you, sir.
Thank
Thank you, sir.
Thank you, thank you, sir.
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 Bye, fellas.